Welcome to the deep dive. We're diving into quantum algorithms today.
Oh, exciting.
It is. And our guide for this deep dive is Jorgo Schneeppert.
Oh,
He
okay.
wrote an essay called, it's actually in German, Quantenalgorithmen. Die Zukunft der Datenverarbeitung.
Okay, so quantum algorithms.
Yeah, quantum algorithms, the future of data processing, if you translate it.
Patchy.
And that's exactly what we're looking at. The future of data processing.
Okay.
And trust me, this is some mind-boggling stuff.
I bet.
Just imagine, like, encryption, the toughest encryption we have today,
Right.
cracked in, like, hours instead of, years or centuries.
Yeah, that's a...
Or designing new materials, atom by atom.
Huh.
Like, think about that. You can
Yeah.
optimize complex systems with, like, unheard of efficiency.
So we're talking about some serious potential here.
Yeah, that's what we're going to unpack.
Okay, I'm ready?
So before we get too deep into it,
Sure.
can you remind us, like, what are classical algorithms and why are they not so good with certain problems?
So think of classical algorithms like, a recipe,
Okay.
a set of instructions step by step that a computer follows.
Yeah.
And they work with these binary digits, the zeros and ones,
Yeah.
to do all these calculations.
Right.
But when you have a problem, like, let's say you need to find the best route between 100 different cities.
Okay, yeah.
It's called the traveling salesman problem.
I've heard of that one.
Even the fastest computers today can take, well, forever, basically.
It's too many possibilities, huh?
Way too many. Yeah.
Like, it's just impractical,
Yeah.
it's not going to work.
And these kinds of problems, they're called NP problems.
Okay.
Easy to check the solution, but super hard to find it.
Okay, so that's where quantum mechanics comes in.
Exactly.
Like, it's here to save today.
Yeah, and Jorgo Schneeppert, he really makes this point in his essay.
Yeah.
Quantum mechanics introduces these kind of crazy concepts like superposition and entanglement. And this allows quantum algorithms to, like, just approach these problems in a totally different way, potentially much faster.
Okay, so let's unpack these quantum superpowers, as you call them.
Right.
Starting with superposition, like, what is that?
Okay, so imagine you have a coin
Okay.
and it's spinning in the air.
Mhm.
It hasn't landed yet.
It's not heads or tails yet.
Exactly, it's both at the same time.
Okay.
That's basically superposition.
Yeah.
A qubit, it's the quantum version of a bit, can exist in multiple states like all at once.
Wow.
And this is, it's based on this wave-particle duality in quantum mechanics, where particles like electrons can be both a wave and a particle. It's pretty wild.
So it's not just an analogy, there's actual physics behind it.
Oh, yeah, absolutely.
Okay, now entanglement.
Okay.
This one always seems, well, a little spooky, to be honest.
I know, right?
How does that work?
So imagine you have two of these coins still spinning,
Okay.
but now they're, like, linked.
Yeah.
Even if you separate them really far apart, like across the universe,
Right.
when one lands and it's, let's say, heads,
Yeah.
the other one instantly becomes tails.
Like, no matter how far apart they are.
Exactly. It's
Yeah.
like they're communicating instantly,
Yeah.
even though that, like, shouldn't be possible.
That is spooky.
Yeah, Einstein called it spooky action at a distance.
I can see why.
And this entanglement, it's a key part of how quantum algorithms work.
Okay, so we have these mind-bending phenomena.
Right?
But how did anyone even think to use them for computing?
That's where brilliant minds like Peter Shor and Love Grover come in.
Okay, I've heard those names.
Yeah, Schneeppert talks about them a lot in his essay. They were the ones who realized, hey, we can use these quantum effects to create completely new algorithms.
Okay.
Not just tweaked versions of the old ones, but like a whole new way of solving problems.
Interesting. So these aren't just like improvements on classical algorithms. It's something completely different.
Yeah, totally different.
Okay, so tell me more about Shor's algorithm. Or
Okay.
it could, like, really change online security.
Yeah, so Shor's algorithm is all about factoring large numbers,
Okay.
which is something classical computers, they really struggle with.
Yeah.
And a lot of our online world, like banking and e-commerce, they rely on this, on the fact that it's so hard to factor large numbers.
Okay.
But Shor's algorithm, it can factor these numbers like exponentially faster.
Really?
Yeah, so potentially it could make a lot of our current encryption methods vulnerable.
Oh, so that's a bit worrying.
It is, yeah.
Like, is our online world gonna, like, crumble?
Well, not necessarily.
Oh, okay, good.
Because of this threat, people like Schneeppert are talking about it. Researchers are working on what they call post-quantum cryptography.
So like cryptography that's safe from quantum computers. Okay, and how does that work?
Well, it's all about finding new encryption methods that can resist attacks, even from really powerful quantum computers.
So like a cryptographic arms race.
Yeah, basically.
Okay, and what about Grover's algorithm? What's that one all about?
Okay, so imagine you have like a huge database
Hmm.
and it's completely unsorted,
Okay.
and you're trying to find one specific piece of information.
Yeah.
Classically, you'd have to go through every single entry one by one.
Right. And if it's a huge database, that would take forever.
Exactly.
So what does Grover's algorithm do?
Well, it uses superposition to basically search through all the entries at the same time.
Whoa. So like in parallel.
Yeah, exactly.
Okay.
It doesn't make it like instant,
Right.
but it can drastically reduce the time it takes.
So it's not about like finding a needle in a haystack. It's more like making the haystack smaller.
Yeah, that's a good way to think about it.
Okay, that makes sense.
And Schneppet points out in his essay that even though this might not sound as dramatic as breaking encryption,
Yeah.
it actually has huge implications for things like data analysis and machine learning.
Okay, we'll have to dive into those applications later.
Yeah, definitely.
Now I know Shor's and Grover's algorithms are like the famous ones.
Yeah, they're the big ones.
But are there other types of quantum algorithms out there?
Oh, yeah, absolutely.
Okay, cool.
Schneppet mentions some of them in his essay.
Mm-hmm.
The world of quantum algorithms is constantly growing. There's like tons of research going on.
Yeah.
There's one called the Deutsch-Jozsa algorithm.
Okay.
It's a really cool example of how quantum computing can like just be totally different.
Okay, how so?
Well, it can determine a property of a function with just one query,
Okay.
while a classical computer would need multiple queries.
So it's like asking a magic 8 ball a question and getting a clear answer in one shake.
Yeah, exactly like that.
Okay, I like that analogy.
And then there are algorithms like QAOA and VQE.
Those are a bit more of a mouthful.
Yeah, they stand for Quantum Approximate Optimization Algorithm and Variational Quantum Eigensolver.
Okay, and what do those do?
They're designed to solve optimization and simulation problems
Okay.
that are just way too complex for classical computers to handle efficiently.
So they're like specialized tools for really tough problems.
Exactly.
Okay, cool. So we've got these incredible algorithms. That's clear.
Mm-hmm.
But I'm really curious about like the real world
Me
applications.
too.
How are they going to change things?
Yeah, how are they gonna like actually make a difference?
That's what I'm really excited to learn about.
Well, that's exactly where we're headed next.
Okay, good.
Get ready to explore how these quantum algorithms are gonna like reshape our world.
All right, I'm ready for it.
It's gonna be amazing.
Stay tuned as we uncover the exciting possibilities of quantum algorithms. So, we're back and ready to dive into how these quantum algorithms are going to actually impact the real world.
Yes, exactly. Moving from the theoretical to the practical.
Okay, cool. And I think a good place to start is with cryptography and security.
Right?
We already talked about how Shor's algorithm could be a problem for our current encryption methods.
Yes, it's a big concern.
Sinepad really highlights this in his essay, how important this is.
Yeah, he does. He talks about the need to develop what we call post-quantum cryptography.
Post-quantum cryptography. Okay, so like cryptography that's safe from quantum computers.
Exactly.
Okay,
Yeah.
and how do we do that? What are the approaches?
So there are several promising approaches, each based on different mathematical problems that are, well, we believe they're hard for both classical and quantum computers to solve.
So it's like finding problems that that even quantum computers will struggle with.
Yes, exactly.
I'll cover.
So one approach is called lattice-based cryptography.
Yeah.
It's lattice-based, okay?
Imagine a really complex grid, multi-dimensional,
Mm-hmm.
and the challenge is to find the shortest vector between 2 points.
Okay.
It's easy to picture, but incredibly difficult to solve, even for a quantum computer.
Oh, wow.
Another promising area is code-based cryptography.
Okay.
This one uses error-correcting codes to create encryption schemes
Okay.
that are hard to break, even if there are errors, which happen a lot in quantum systems.
So it's like building in some redundancy, right?
Yes,
To
exactly.
protect the information, even if there's like noise.
Exactly.
Okay, that's cool. And are there any other approaches?
Yes, there's also hash-based cryptography, which uses cryptographic hash functions
Okay.
to provide digital signatures.
And Schneppet seems optimistic about these approaches.
He does, but also cautious.
Right. So it's good that people are working on this, that there's awareness.
Definitely, it's a very active area of
Yeah.
research. Okay, so cryptography is one area where quantum algorithms could have a big impact.
Right.
But Schneebot also talks about optimization and simulation, right?
Yes, he does.
And that seems really exciting because it touches upon so many different fields.
It does, yeah, like logistics, energy, manufacturing, even drug discovery.
Okay, I'm definitely intrigued. Tell me more.
So imagine a world where we can optimize delivery routes down to the minute,
Okay.
reducing fuel consumption and, making deliveries faster,
Right, yeah.
or being able to design new materials with like amazing properties
Wow.
by simulating their molecular structures at the atomic level.
So it's like taking efficiency and innovation to a whole new level.
Exactly.
But how do quantum algorithms, how do they actually do this?
So remember those algorithms we talked about earlier, QAOA and VQE?
Okay, remind me.
Okay, so QAOA, the quantum approximate optimization algorithm, it's a hybrid algorithm.
Okay.
It combines quantum and classical computing to solve optimization problems that are just too complex for classical computers alone.
So it's like a quantum-assisted approach
Yes,
to find the best solution or close to the best solution.
exactly.
Okay, and that could be used for like scheduling, logistics, financial portfolio optimization.
All sorts of things, yeah.
Wow.
And then VQE, the variational quantum eigensolver,
Yeah.
that one is particularly good for simulating molecules and chemical reactions.
Okay, so this is where it gets really interesting, right? Because Schneepat talks about how these algorithms could really accelerate drug discovery and materials design.
Exactly. By simulating how molecules behave, we can design new drugs, create more efficient catalysts,
Mm-hmm.
develop new materials.
Wow, it's like having a quantum chemistry lab
Yes, exactly.
at our fingertips.
At your fingertips, yeah.
Okay, Schneepat also mentions that quantum algorithms could help us solve problems that are like impossible for classical computers.
Yes, he does.
What are some examples of that?
So, for example, simulating the behavior of complex proteins.
Okay.
That's really important for understanding diseases and developing new therapies.
Right.
But even the most powerful supercomputers today, they struggle with this.
Yeah, it's just too complex.
Way too complex.
So quantum computers could really be a breakthrough here.
Yeah.
And what other fields could be impacted in this way?
Well, Schnippe argues that we're really just starting to explore the possibilities,
Mm-hmm.
but feels like artificial intelligence and machine learning could also be revolutionized.
Okay, so like quantum AI.
Exact.
That's amazing.
Imagine using quantum algorithms to analyze data, recognize patterns
Right.
much faster and more efficiently than we can do today.
So like giving AI a quantum boost.
Exactly.
Okay, so we've got cryptography, optimization, simulation, AI. It seems like quantum algorithms could touch almost every aspect of our lives.
It really does seem that way.
And Shepard also mentions finance, right?
He does, yeah.
As a field that could be disrupted.
Yes, quantum algorithms could really change financial modeling, risk management, portfolio optimization.
Okay, so Wall Street meets quantum mechanics.
Yeah.
How would that work in practice?
So imagine running complex financial simulations on quantum computers
Okay.
to get more accurate risk assessments, optimize investments,
Right.
or maybe even use quantum algorithms to find arbitrage opportunities
Yeah.
or predict market trends.
So it's like taking financial modeling to a whole new level.
Yes, exactly.
Okay, so we've explored all these potential applications.
Yeah, a lot of potential.
And it's clear that quantum algorithms have a lot to offer.
They do.
But as with any new technology, there are also challenges
Of course.
and limitations.
Absolutely.
So let's shift gears now and dive into those challenges and uncertainties that lie ahead. So we're back for the final part of our deep dive.
Yeah, time to get real.
Right, we've talked about all these amazing possibilities, quantum algorithms changing the world, you know.
Revolutionary stuff.
But Yurgo Schneepat, in his essay,
Yeah.
he also acknowledges that there are challenges.
There are, for sure.
Like the road to this quantum-powered future,
Right.
it's not going to be easy.
Not at all, no.
So let's talk about those challenges. Where do we even begin?
Well, I think one of the biggest ones is just building these quantum computers
Okay.
and scaling them up.
Right.
Because right now, they're incredibly sensitive.
Yeah, I've heard that.
They need these, like, super controlled environments,
Mm.
often at these ultra low temperatures,
Yeah.
shielded from any kind of disturbance.
Right. Like, even the slightest vibration can mess things up.
Exactly. It's like, I've heard it compared to building a house of cards in a hurricane.
Oh, wow. Yeah, that's a good one.
The slightest, puff of wind,
Yeah.
and the whole thing collapses.
And the qubits, those are the building blocks of quantum computers, right?
Right. They're notoriously fragile. They need to be kept cold, isolated from noise,
Mm.
controlled with like incredible precision.
So it's not just about building bigger quantum computers. It's about making them more stable,
Exactly.
more reliable.
Yeah, exactly. And that brings us to another big challenge, which is error correction.
Okay, right, because I've heard that quantum computers, they're very prone to errors.
They are, yeah.
So how do we deal with that?
Well, developing these effective error correction methods, that's crucial if
Yeah.
we want to make these quantum computers actually useful.
Right, it's like trying to write a message on a chalkboard and someone's constantly erasing it.
I like that, yeah.
You need a way to like keep the message there.
Right, so quantum error correction, it's all about encoding information
Okay.
redundantly across multiple qubits.
So like having backup copies.
Yeah, basically, so that even if some parts get corrupted,
Right.
you can still retrieve the information.
Okay. That's clever.
But it's not easy to do.
I can imagine.
And it requires a lot more qubits.
Right. So it adds complexity.
It does, yeah.
Okay, so building this large-scale, fault-tolerant quantum computer,
Right.
it's a huge engineering challenge.
Yeah, it's a massive undertaking.
And Schneepat really emphasizes this, right?
He does. He talks about how it requires sustained investment, constant innovation,
Yeah.
collaboration across different fields.
So it's a really big scientific project.
It is, yeah.
But it's not just about the hardware, is it?
No, it's not.
There are also like theoretical questions that
Right.
need to be addressed.
Absolutely, yeah. Like, for example, developing new quantum algorithms.
Okay, so we're still figuring out the best ways to use these quantum computers.
Yeah, exactly. There's a lot of potential, but we're still exploring.
Like, we have this powerful tool,
Right.
but we're still learning how to use it.
Exactly.
Okay, and there are also questions about like the limits of quantum computation.
Yes,
Like, which problems are actually best suited for quantum computers?
that's a big one.
We don't fully understand that yet.
No, we don't.
So it's important to be realistic
I think so, yeah,
about what quantum computers can do.
definitely.
Schneepat, he advocates for this balanced perspective,
He does, yeah.
recognizing both the potential and the challenges.
Absolutely.
So we've talked about the technological challenges, the theoretical challenges,
Right.
but there are also broader societal and economic implications
Oh, yeah, for sure.
of quantum computing.
Right, as it becomes more powerful.
Yeah.
It's going to affect our lives in many ways.
And Schneepat talks about this in his essay.
He does, yeah.
What are some of the areas we should be thinking about?
Well, one of them is jobs.
Okay.
Because as quantum computers get more powerful, they could potentially automate a lot of tasks.
Right, that are currently done by humans.
Exactly.
So there's this concern about job displacement
There is.
in certain sectors.
Definitely.
So we need to like prepare the workforce for this quantum era
Absolutely, yeah. Education and retraining programs, those are going to be crucial.
to help people adapt.
Yeah, to thrive in this new world.
And Schneepat also mentions the potential for misuse of quantum computers.
Right. He does bring that up.
Like any powerful technology, it can be used for good or for bad.
Exactly. Yeah, it's a double-edged sword.
So we need to be aware of that
Definitely.
and think about like ethical guidelines
Absolutely.
for the development and use of this technology.
To make sure it's used responsibly.
Right. And then there's also the question of access.
Yes, that's a big one.
Who's going to have access to this technology?
Right.
And how do we ensure that the benefits are like distributed fairly?
Yeah, it's about equity.
Right. We don't want to exacerbate existing inequality.
No, definitely not.
Schneepat really underscores these points.
He does, yeah.
He wants us to think critically about the impact of quantum computing. So we've covered a lot of ground here.
Yeah,
The
yeah.
challenges, the uncertainties, the potential risks.
So a lot to take in.
But I still feel like there's this excitement
I know what you mean.
about the possibilities.
It's hard not to be excited.
Quantum computing, it's a frontier
It is.
of scientific exploration.
Of a whole new world.
Yeah, and it could help us solve some of our like biggest problems.
Exactly.
So as we wrap up this deep dive,
Yeah.
what would you say is the key takeaway for our listeners?
Well, I think quantum algorithms represent a fundamental shift in how we think about computation.
Yeah.
They have the potential to change so many industries
Hmm.
and solve problems that we can't even solve today.
Right, but the road to this quantum-powered future,
Right.
it's going to be challenging.
It is,
We
yeah.
need investment, we need innovation,
Hmm.
and we need to think carefully about the societal and ethical implications.
Definitely.
And maybe most importantly, we need curiosity,
Oh, absolutely.
a willingness to embrace the unknown,
Yes.
and a belief that we can, use this technology for good.
Couldn't have said it better myself.
Well, thank you for joining us on this incredible journey
My pleasure.
into the world of quantum
It's
algorithms.
been fun.
And to our listeners, thank you for diving deep with us.
Yes, thank you.
Keep exploring, keep questioning,
Stay curious.
and we'll see you next time.